Stefanie Tellex is an assistant professor specializing in robotics at Brown University. Stefanie, welcome to Software Engineering Daily.
Thanks.
The goal of your research is to construct robots that seamlessly use natural language to communicate with humans. How close are we to that goal?
I think we're a long ways away from realizing that vision. The challenge is that language can be used to express such a large variety of concepts that it's really hard to create systems that can interpret language with the robustness and the breadth of understanding that a human brings to the task.
So you write that in 20 years, every home will have a personal robot which can perform tasks such as clearing the dinner table, doing laundry, and preparing dinner. Do other people in your field agree with that timeline?
There's a lot of diversity in estimates on how long things are going to take, and I would definitely put a lot of variance myself on that 20-year number. And we've already seen robots enter the home in the form of the Roomba and other devices that focus on specialized tasks like cleaning floors. And there's also been quite a lot of robotic toys of various types that are in many homes around the world. I think I think that as robots become more general purpose, there's going to be a larger and more pervasive presence of these systems in our lives. So the places where they're being successful today, and even right now today, are where there's a really specialized task, like the Roomba, or something like telepresence has seen, like the Vigo or Suitable Technologies Beam. These are existing platforms that you can buy today, and they're deployed in offices and homes, and they work. They're really cool. Like the Beam is awesome for telepresence, for example.
Is that what Edward Snowden uses?
Yeah. I think it's the Beam is the one he uses. Yeah.
Okay.
Yeah. So the timeline on these. The sort of dream of AI almost is like these general purpose machines, C-3PO from Star Wars or something like that. And maybe 20, there's definitely people who would say 20 years is way too optimistic. It's going to be 50 or 100. There's also people who would say that's way too pessimistic and we're going to see these things in 5 years. There's a big push for deep learning right now, for example, that maybe is going to solve all the problems. The Google self-driving car folks are planning to be on the market, soon, right? Like in 5 or 10 years or something is what you hear. There's a lot of disagreement about whether that's actually realistic or not.
You won the Best Paper Award at the Robotics, Science, and Systems Conference for a paper called Asking for Help Using Inverse Semantics. What events led to you working on this problem?
So I was working in collaboration with Ross Nepper, who's a co-author on that paper, and he had created a really cool robotic system that could autonomously assemble IKEA furniture. So this was a team of robot mobile manipulator robots, U-bots, that could assemble a table by screwing the parts and putting things in. And it's really cool. If you haven't seen the video, you should definitely watch the robots doing this task. But what we noticed, when we started talking about his system, you can make a video of a system like that, but when you actually try, the video, and this is true of many robotic systems, behind the video, there might be 100 or 1,000 outtakes that didn't make it into the video where something went wrong. Sometimes things that aren't even really your fault, you just got the bits were flipped the wrong way or something, and it just didn't quite get that screw into the screw hole, or your motion capture system crashed, or you lost power and the whole thing rebooted or something. And this is incredibly frustrating because the user doesn't, the person who's trying to use the robots for something, they don't care why it didn't work. The robot's broken, it didn't work. And so we realized that this was a challenge because I think this is sort of the barrier to general purpose robots, is this sort of long tail of problems, of things that can just go wrong that aren't what you expected. It's really, you said it's a software engineering blog, we know about test cases and stuff, unit testing and that. But in a robot, a unit test involves moving things in the physical world and setting things up and tearing things down in the physical world. So it's really hard to get that level of robustness in a robotic system. It's really challenging. And so what we realized is that, we could make progress towards this vision of robots operating in unstructured environments by accepting that things were going to go wrong and then thinking about how we could recover from those types of failures. And in particular, we thought that in many instances, there's relatively simple and easy actions that a human could take, even a human who wasn't a roboticist and didn't really know about the robots. But the problem was they didn't know what they should do to help the robots or to get them unstuck.
So in most cases when a robot encounters a problem, does the robot know what went wrong, or does it just know that something went wrong?
It varies. So in many instances, it knows there'll be something that it's expecting that isn't there. So like, for example, if it's assembling a table, it needs to have the table legs, and it's expecting to have those table legs. And so it may not know where the legs actually are, but it can still at least say, well, I need a table leg to continue moving forward. In other instances, it might know where the table leg is, but it's like out of reach. It's on a table up out of reach or something like that. And then it can provide more information to the person. Like, can you hand me that table leg that's up on the table, that's out of my reach that I can't get?
Okay. But before the robots even start assembling a piece of furniture, these robots use a strips-style symbolic planner. Can you describe what a strip-style symbolic planner is? Yeah,
it's basically creating a formal model of the task that the robots are trying to complete. So it formalizes the process of assembling the table as a state about which parts have been put together and which parts haven't been put together and where they are in the world, and then actions that the robot can take. For example, picking up a leg or the base of the table, or screwing something into something else, or flipping the table over. And then the effects of those actions. So after the robot has screwed in one of the legs to the table, after that it's attached to the table, and it can go on to the next step in the plan.
So how does the robot enumerate those states?
So it has to search through the different ways it can attach things together. So part of the knowledge that's encoded in the effects of its actions is what does it mean for the table to be assembled, like a goal condition. And then it does pick your favorite search algorithm to, breadth first search or something to find a path to achieve the goal. There's some tricks that they had to play because you have this combinatorial problem with all the different wrong ways you could put the table together. And that was one of the things that Ross was working on in the IKEA furniture assembly.
So you can often get into a situation where this robot encounters a problem, doesn't really know what went wrong. When you first started working with Ross, what was the way that he was having the robot disambiguate that?
Well, at first it was just a bug, right? So it wasn't like they would try to recover. The precondition wouldn't be met.
Oh, they just start over.
And yeah, you start over, or Ross goes and fixes it. That was actually one of the things that inspired us to work on this. Was we were both realizing that many, many, many times we would help our robots. Like, we would watch the system, Ross would watch the system, see something was wrong, and then somehow intervene in order to reboot something or restart something or move the table leg so that it was in the right position or something like that, so that the robot could continue. And we realized that this was actually essential in many instances to making the system work. But it was bad because if you imagine scaling this up to many robots at once, there's only one of Ross, and only one robot. There's many fewer roboticists. So the idea was, how can we enable robots to benefit from this type of help without requiring a roboticist who knows the system to be in the room and observing what's going on.
So if a robot realizes that it needs to ask a human for help, how does the robot phrase its request? Or what types of different help can the robot ask for?
Yeah, so we thought about that as designers. So we basically looked at the model, the strips model that the robot was using in terms of furniture assembly, and we ran the system a lot and wrote down the different ways that we had observed it failing. And then gave the robot a grammar of different types of requests that it could make to recover from the different conditions. And then the contribution of the paper was you can write down this grammar, and that restricts the space of things it can say quite a lot, but there's still a very large set of actions, words and sentences that the robot can say. And it really depends which one is correct, really depends, or will be most effective, depends on the environment that the robot is in, and where all these pieces are and where it is in the plan. And you really couldn't enumerate them or write down a fixed rule to generate those types of requests. So we created an algorithm that lets the robot dynamically compute how effective different requests for help will be by assessing how interpretable they are.
You've said that the communication between robots and humans is a problem that's rooted in both linguistics and philosophy. How did that overlap between linguistics and philosophy, how did that manifest in your decision for how to make this asking for help model?
It's interesting because a lot of what's powerful about language is not language itself, but how language connects to other aspects of the world. And so our model for asking for help was specifically about that connection. So what we wanted to do was decide what the robot should say based on how interpretable that was and how ambiguous the particular sentence was. So for example, if there was just one table leg in the environment that it can't reach, the robot could say, hand me the white table leg, it's short, it's sweet, it's easy to understand. But if there was, and that's what it should say, but if there was a bunch of table legs, one of which was out of reach and the other ones weren't, then it needs to give more information because otherwise the person might not understand which one it's asking for and why. And the way that we decided to model that is by creating a mathematical model of how the person would interpret the sentence. And this was inspired by work in cognitive semantics, Herb Clark's work in terms of how people communicate language by trying to think about how the other person is going to interpret what they're saying. And we translated this into a mathematical system for quantifying how easy or hard it would be to interpret the sentences that the robot was considering saying.
So why do we need a mathematical framework for communicating with robots?
I think one of my goals is to understand in a very general way what it means for a human and a robot to collaborate. So you can imagine these very general purpose robots that are operating in unstructured environments on a very large variety of tasks. It's not going to be possible for a programmer to be able to design specific language interfaces, let's say, for each of the tasks, because the space of things you might want the robot to do is so large that it's impossible to do it. And you can sort of imagine like Windows or something, but worse, because like in terms of all the different things that could happen. And so one of my goals is if we can formalize a mathematical framework that's general enough, we will be able to have a unified way of thinking about collaboration, so that as you add more capability to the robot, and more knowledge about how people interpret the world, it will be able to sort of scale up its communication and collaboration abilities.
Did these robots have a model for their human helpers and what their humans are capable of interpreting?
Yes, exactly. So in the asking for help work, that's exactly what we did. We endowed the robot with a model. It's imperfect, of course, but a model of how the person would interpret the request. And we actually showed that by using this model, we were able to generate more effective requests for help than other approaches, using templates, for example.
So does the robot learn over time how to interact with a specific person, or is it not that general?
It's not that general yet, but the model is trained from data. So we collected data sort of offline of how people interpret language to create a model for basically the mapping between words that the robot might say or the person might say and actions in the world. And then we use that model to generate requests for help. And you could definitely imagine doing that in an online kind of way, where as you observed more things from the person, you would go back and update the model. But in that particular paper, we did it kind of in batch mode. So we did the learning first, and then once we had learned the word meanings and the commands, then we did the evaluation.
Could you describe that learning process in more detail? I'm very curious about that. As much technical detail as you want to go into.
Sure. So basically, this is really from an earlier paper about interpreting language, natural language commands. So basically, the idea is you need to go from words like hand me the white table leg to actions that you want the robot to take. So you need to map between the words, the white table leg, and some object that's out there in the world. the actual table leg that you're supposed to pick up. And then you had to map between the words pick up the white table leg or pick up whatever you're supposed to pick up and an action, a physical sequence of motor commands that either the robot or the person, because you could do it in both directions. The person could be telling the robot what to do, or in this paper that we were talking about, the robot would be telling the person what they wanted to do. So to do this, we collected, the first thing we did was collect a lot of data in the direction of the person saying something and then the robot doing something. So we collected a lot of examples of the people saying things to our robots and then action sequences of the robots following those commands using Amazon Mechanical Turk.
Okay, so that's the mapping. You were doing mappings.
Yes, right. Examples of what this mapping looks like. And then using this data, we defined a mathematical model that factors according to the compositional structure of language. This is the generalized grounding graph in one of our earlier papers, the 2011 AAAI paper. So we created a mathematical model that factors according to the structure of language, and we trained the model parameters using this batch data, this data that we collected of language paired with actions. And then once we've created the model, you can use it either forwards or backwards. You can use it for understanding or generation of language. So we showed in our first work was understanding. So we showed that you could using this model, you could get a command like pick up the tire pallet or put the white table on the ground next to the table and translate that into actual motor commands that the robot would execute to interpret the command. And then the RSS paper was the inverse problem, inverse semantics, right? So using the same model, we could basically say, instead of understanding language, we're going to use the same model for understanding, for modeling how the person would interpret what we're thinking of saying in order to pick the most interpretable thing to say. And so we had one very powerful model that could do both tasks.
You've mentioned this generalized grounding graph, and I would like to go into that further. Could you first discuss the concept of a grounding and define that?
Yeah, so grounding is a concept from philosophy. So Simon Harnad, I think. I don't remember his first name. Harnad introduced this idea of the symbol grounding problem, which is mapping this idea that words aren't just words, like they actually connect to something non-linguistic out there in the world. Perceptual data and motor data, things that you can see and hear and feel and do. And in order to enable a robot, which it needs to take physical actions in the world, in order to enable a robot to interpret words, you need to capture this mapping. And the term that he used to describe this is grounding. So the words have to be grounded in the world. They have to somehow map to stuff that's out there in the world.
So with that said, what is a generalized grounding graph?
So the generalized grounding graph was our mathematical framework for describing how to do this mapping. So it's a probabilistic graphical model. It's basically formalizing if I say constraint satisfaction problem, I don't know if that it's formalizing the inference problem that you need to solve. So if I say pick up the tire pallet or pick up the white table leg, in order to interpret that, the robot has to, it kind of breaks down into subproblems. First I have to know what the white table leg is, and then I have to know what I should pick up. Like once I figured out that it's the white table leg that I'm supposed to do something to, I have to figure out, should I pick it up? Should I move it somewhere? Should I flip it over? Should I paint it? Whatever, all the things the robot could do, it needs to figure out which one is going to do. And it's not just pick up the white table leg, but you might say pick up the white table leg that's on the black table in the corner. Well, now I've got to figure out the corner and the black table, and then the white table leg that's on the black table, and then pick up or put or play or whatever they said, and how that all fits together. So as I add more complex commands and as I understand diverse commands, the model, you can't just have one fixed template model for what the robot should do, but it has to reflect the compositional structure of language. The fact that I can add more clauses, I can, the cat that ate the rat that ate the cheese, you can keep going, forever adding more clauses to this. And the generalized grounding graph model basically formalized this problem by saying, look, there's this structure for language, which is well known, and we can extract the structure, and then we can systematically create an inference problem with variables that we have to fill in. So we have to know that there's a white table based on the structure of language, which we can extract with a parser. we know that there's a white table leg, and we know that there's a black table, and the white table has to be in the corner on the black table, so there's some relation between the two. So you get these constraints. This X has to be on Y, and X has to be a white table leg, and Y has to be a black table, and the robot is supposed to pick up X, let's say, or put X in the corner, or put X, which is on Y, in location Z. So you have all these constraints that it's inferring, and the framework basically says if you take the structure of language, you can write down this inference problem, learn the meanings of words, so learn how to recognize the white table leg among all the other objects in a pretty general way, and combine it all together in order to get actions for the robot.
So you mentioned the mechanical Turk training process that you used, and I thought that was a very fascinating application of mechanical Turk. Maybe it was straightforward to you, but I would love if you could explain how you used mechanical Turk in more detail.
Yeah, so we use it for a lot of our work because it's really helpful to have data about what people want the robot to do and what people will say to robots, and even if it's almost a thought experiment or something. So for the Turk data, a lot of what we've done is we flip things around. So what we want is people to say things and then the robot does something. But it's kind of hard for a Turker to operate a robot. So our earlier work was the robotic forklift, and our later work was with these U-bots, these manipulator robots. And you can imagine keyboard and mouse interfaces for driving these platforms around. Of course, you could get behind the wheel of the forklift and drive it around, or if you wanted to crowdsource it, you have to make a sort of simulated interface. But it's definitely not a straightforward thing, and it might be kind of confusing to have to learn how to use the interface that we created for driving the forklift and making it do different actions. And it may also not be all that realistic, depending on how. If you give them really low-level control of the forklift, it can be quite challenging. So because you have to, how far back are you going to tilt the forks? You're in a screen, so you can't hear things, you can't see things. In the case of a U-bot, if you're an arm, you might have 5 or 7 degrees of freedom on the joints of the arm, and direct control is moving all those joints. It's pretty hard to do for a human to do direct joint control. So instead, we flipped it around. We said, okay, we're going to come up with actions. Either randomly, we're going to use our system to sample things the robot could do, or we're going to drive the robot because we know how to do it, and create videos of the robot doing sort of useful things. So for the forklift, it was moving pallets around a warehouse. For the RSS paper, where it's assembling furniture, it was different types of assembly tasks, screwing things in and picking things up and moving them around, handing things off to the person. So we created videos of the robots doing these tasks, and then we showed the video to somebody on Amazon Mechanical Turk, and we said, pretend that what you wanted the robot to do was this video. And everybody saw the same video. And then we said, come up with a set of natural language instructions that you would say as if you were talking to a person to get them to do the action in the video. And in that way, we kind of had a common grounding, which was the video, what the robot was doing in the video. And then we collected many different examples of how people could describe the actions that they were seeing.
Does this exemplify corpus-based training?
Yes, this is the process we used to collect a corpus or a data set of natural language commands paired with groundings, actions, and objects and places in the world that map to them.
Do humans also learn through corpus-based training?
That's a good question. So I have a 2.5-year-old son, and he has far surpassed my robot in both his language use and his abilities to manipulate objects in complex environments. But at the beginning, my robot, was more capable than him in many ways. So when he came out as an infant, he really couldn't pick things up. He couldn't talk. He was kind of doing a lot of flailing around. And I think that a lot of what happened over the 2 years or 2.5 years until now part of it is growing and developing, but I think a lot of it could be described as data collection. Experimenting with what happens when I do this, what happens as I flail around, and then gradually building more complicated capabilities, more purposeful types of manipulation and perceptual experiments in order to become more and more capable. So one of the directions we're going now in my group is trying to think about how we can give a robot access to the same type of data and enable it to learn over time how to manipulate objects and interpret commands and get better over time and leverage that data, that experience to do better.
So how does creating a child compare to creating a robot, like in terms of gratification?
Well, my son is the most important thing in the world to me. So I definitely, it's really hard to compare them, but like Jay is, I guess I have to say Jay is my son is Jay is the most important thing. But robots are pretty awesome too. And when I'm not with Jay, I'm with my robot. So I'm pretty fortunate to have such awesome ways to be spending time.
Do you think like in a distant future when we can actually like create sentient robots that have some intelligence that is of the level of a child, it will become like increasingly marginal to have a kid rather than to just have a computer that simulates the...
Oh, I don't know. I mean, I used to not want kids, and now that I have a son, like it is the most rewarding experience of my entire life. And I think a lot of that is like, biological, like evolution and oxytocin is a powerful thing, right? And I think it will be hard for a robot to replace that. But, I don't know. I mean, I think it's hard. Our families are who we are, right? Like it's part of what makes us human. So I don't think that we're going to see a robot take their place. These are tools, I mean, people personify their cars. People name their Roombas. We have pets and stuff too. But like, when you have a kid, like there's nothing like it in the world.
But the way that you described it was kind of like if the primary benefit that you've gotten from the kid is like this oxytocin, this biological thing, then it's basically just a tool to get oxytocin, right? I mean, not that there's anything wrong with that.
Yeah, right. I mean, so I think like if you're going to be really cynical about it, I mean, addictive drugs, okay? So like, there's substances that we can give ourselves that directly stimulate the pleasure centers in your brain, and somehow people don't seem to be very satisfied with that. I mean, some people use those substances, but we as a society generally don't approve of drugs. Many of them are outlawed, for example, and we have rehabilitation programs. And I think, there's a spectrum of these types of things, like TV and web browsing is some kind of addictive thing that maybe isn't quite so good as other ways you could be spending your time. So I don't know. I mean, we're complex beings that are motivated by many factors.
But those things have diminishing returns, whereas having a kid does not really tend to. In my understanding, it doesn't really have diminishing returns. Like if you're a drug addict or a web browser addict, like those activities have diminishing returns. But having a kid seems to like, I don't know, maybe not have diminishing returns. So maybe that's why it's a more I don't know. Society is more sympathetic with people that want to have kids rather than considering it an addiction.
Yeah, I mean, I think it's part of what makes us human, like the relationships that we have with other humans and kind of passing things forward to the next generation. But it's really, I mean, different people have different opinions about this. And it's one of those things that I think is just very personal. It's a very personal decision whether or not to have kids. And many cultures have very widely different baseline beliefs and practical beliefs, about children and how they're raised and what happens to them and when you have them and when you don't have them. Our most contentious issues are about that stuff. So
yeah. I mean, I myself, I haven't really decided one way or another, but it's hard for me to even develop a framework for thinking about it.
Yeah.
So anyway, back to IKEA robots. There's a term that you use in your paper called inverse semantics, and you touched on this a bit earlier. Some listeners probably don't know what inverse semantics is, so could you first define forward semantics?
Yes, right. So inverse semantics is a term we introduced in the paper. And the idea is, so forward semantics is basically the problem of understanding language. So you're a robot, and the person says something to you, and your job is to figure out what you should do in response. So that's the forward semantics problem. You hear something from the person, you look at the world, and then you try to figure out what actions you should take to follow those commands. So then inverse semantics is the other way around. You're the robot, you want the person to do something to help you, right? Something's wrong. So you have something in mind that you want the person to do. And you're trying to figure out what words should you say to the person in order to get them to do what you want them to do. And so this is the inverse problem, right? You're not listening to something and then doing something. You've got something in mind that you'd like to see done, and you want to say something to the person and find the words to get them to do it. And so this is why we called it inverse semantics, because it was the other direction from understanding.
So what are the, could you compare and contrast the strengths of using forward semantics versus inverse semantics?
Well, they're not, they're not competing with each other. They're different things. Like, so if, you want a robot that can do both, right? You want a robot that can understand language, and you'd like the robot, if it encounters problems doing what it's told, you'd like it to be able to explain those problems to you. You'd like it to be able to ask for help when it needs help. So they're kind of like two sides of the same coin.
Okay, so if I understand this right, forward semantics is the act of finding groundings in the real world which map to natural language, and inverse semantics is finding natural language that maps to groundings in the real world?
That's right.
Okay.
Yep, that's exactly right.
Okay. And so there was your approach seeks to unify natural language generation and natural language understanding. Why are language generation and language understanding two separate fields? Could you draw the distinction between those two?
Yeah, it's a really good question. So the reason is that generation is often very much simpler problem than understanding. So for language generation, often you're doing it in a context where many, many things are under your control. So you're doing it, for example, you're writing an email to somebody advertising something, the same thing, you just change the name, right? You have some kind of template and you switch it and you switch which one you do. Or you're making a confirmation page, that's all language generation. For like you're buying something on Amazon, you see the confirmation page, it says what you've bought. There's slots for what you bought and where it's going. You fill in those slots and you're done. So for many applications, the generation problem is so constrained that it doesn't really make sense to tie it to some complicated understanding system. You just want it to fill in these slots and move on with your life. But in the robotic setting, it's not the case, because the environment in which the robot operates there's so many potential environments in which it could be that a template-based approach, it'll get you a part of the way there, and that was one of our baselines, where we basically, in the different situations, we wrote down a template for what the robot should say. But what we found is that there were so many different environments and configurations of where all the blocks could be, that a template-based approach would hit situations where it would still generate ambiguous commands. But we then added this extra power of figuring out what extra stuff to say based on interpretation and by modeling the interpretation, and that allowed the robot to generate more nuanced commands, so adding extra disambiguators when necessary, but not when it didn't need them, and people found that easier to interpret.
Can you describe more about the difference between how a robot perceives the world versus how a human perceives the world? Like, what about robot perception is unintuitive?
A robot is very impoverished perceptually compared to a person. And that's one of the biggest limitations in robotics today is perception of the environment. So a robot, partly it depends what sensors you've got, but like a typical mobile robot might have a LiDAR, which will give you kind of go, no-go information. I can drive here and I can't drive there. It might have a camera, but computer vision is really hard. So it's getting images from the camera, but it might not be able to know that's a chair and that's a table and that's a light switch, because it's really hard to do that kind of labeling. We're seeing a lot of progress right now today in that, but even so, like, a good system might do chair detection and get it right 70% of the time. And that means 30% of the time, you're not going to see the chair. You're not going to know what it is. It's going to be this smeary blob, or you're going to think it's something else. And so, and then aggregate that over all of the things a person could be asking you about. Move all of the chairs in the corner by the table and clean up all the laundry and put it in the closet. And if you don't know what laundry is and where the closet is, you'll be in trouble. So a lot of work in robotics, particularly, for example, in the inverse semantics paper, we sidestepped the whole perceptual problem completely using a motion capture system, a Vicon system. So we basically had an instrumented environment that enabled us to know about just the objects that the robot cared about and nothing else.
In the prototypical experiment that you were running, you had a human engaging with a robot to build an IKEA table. And the human would ask the robot, "Please hand me the white table leg." Is the human phrasing his language in a way that he knows the robot will understand? Like, does he know that there is already this mapping within the robot that says, "Please hand me the white table leg"? Or to what degree is the robot disambiguating that sentence?
We constrained things in our data collection in the first place by showing them videos and then having them generate instructions. But we found that one of the biggest limitations in our system is that when you actually put it in front of a person, they really don't stick to the types of scenarios that you imagine during your data collection. It's very easy for them to slip outside and start talking about things that the robot simply can't see or doesn't know about. And that's a challenge because the language, for example, in our forklift work, somebody gave instructions for how to pick up a dime like a coin with a forklift. And the way that you do it is you bring the forks on top of the dime and then you lower it slowly and then you slowly drive backwards and it flips backwards onto the fork. Does that kind of make sense? You lower the fork on top of it and then the friction.
That sounds really meticulous for a forklift.
Yeah, human operators can do it. You can look on YouTube and see them doing it. And they sent us these instructions describing what I just did, and we could see it. Like, we could imagine doing that, going out in the forklift and doing that. But our system had no chance of interpreting those instructions because we just didn't give it those really low-level, fine-grained actions about moving the dime. And if we had given it those actions, the problem is that the space of possible actions would be ginormous because you could, at any moment, like, you might be told to unload the truck, and we're searching and like moving the forks up a couple of inches, and we'll never find these high-level actions. So one of the thrusts in my group now is to create new methods for planning in these types of state spaces that effectively map to different levels of abstraction that people might use. So this is our Minecraft work.
Minecraft work. Okay, can you discuss that in more detail? I did not read about any Minecraft work.
Yeah, so this is one of the newer projects in my group. So we haven't gotten it all out there yet. But like, the idea is we wanted to start to think about planning at multiple levels of abstraction. And one of the domains where this comes up is in simulation and in Minecraft, basically. So have you played Minecraft?
I actually haven't.
Oh, really?
I know. I think it's a sign of my age.
It's a great game. It's one of the most popular video games of all time.
I know.
It's awesome. And it's challenging. And the reason it's challenging, especially from an AI perspective, is that you can literally destroy any block, or unless there's bedrock, but like, any block around you, you can destroy it and you can place it anywhere. And so you can build arbitrarily complex structures. People have done, if you've ever seen the videos of like,
oh yeah,
it's crazy. Like the castles and,
calculators,
yeah. That's one of the things that inspired me, actually, was watching the Redstone calculator, graphing calculator, CPUs and ALUs and stuff. It's really mind-blowing what you can do in this game. And AI and one of the things we realized is it's really hard to make an AI make a graphing calculator and really engage in the full space of what you can do inside of Minecraft because of this combinatorial explosion of all the different actions. So like, if you take as your primitive action moving around, mining blocks and placing blocks, most of that space is throwing blocks randomly around and, zombies kill you the first night. But then there's this really rich space of actions, building structures and, going all the way up to calculators. and sort of taking over the whole world and sending and all this stuff. So we are using this as a test bed for our algorithm. So we have another paper about learning how to play Minecraft through experience. So like learning about the types of actions that are good ideas depending on what goals you're trying to achieve in Minecraft. And we've actually released a mod for Minecraft as well that lets you plug in different AI algorithms and use them to control an agent, a Minecraft agent. It's called Burlapcraft. You can try
That's
it out.
super cool. I will need to put that in the show notes. So you mentioned Minecraft, you mentioned the IKEA, you also touched a bit on the robotic forklifts. Could you talk about how you got involved in robotic forklifts?
Yeah, I was a postdoc at MIT, and I was collaborating with the people who had sort of made the forklift project. And basically, the team that started that project had competed in the DARPA Urban Challenge. So that was the self-driving car competition. And coming out of that, they wanted to build on what they had achieved in the Urban Challenge with the self-driving vehicle, but they wanted to have it be more complicated. And at the same time, the Army was really interested in automating forward bases. So you may have like a warehouse and a forklift at these bases managing the supplies. And if you can get a person out, if you can automate the forklift, that's less people in danger and cheaper, and things are more efficient. So they created this project to create an autonomous forklift. And it was interesting because they had done a lot of visits to these bases to understand the workflow and how a human forklift operator fit into the workflow of these areas. And so then so then I was fortunate to be able to interact with them and realize a lot of what happened is that people would talk to the human operator and ask them to do different things. And that's sort of what got us started on exploring different types of language interpretation for the forklift.
So I'm curious about the nature of robotics research in academia versus industry.
Yeah.
Do you feel like you're doing research in academia that you would not be able to do in industry?
Definitely. I think part of it is sort of how far ahead are you looking? So in industry, it tends to be really driven by a product or a concrete goal that, is 5 years out at most. Whereas, we talked about, is it 20 years, maybe it's 50, maybe it's 10, but like, it's definitely not technology that's going to be out there tomorrow. But on the other hand, I find it very exciting because if we can actually get this to work, the impact is immense. And trying to figure out, like, what are the roadblocks, what are the problems that we have to solve to really enable this type of technology, and then solving them is, I think, part of what needs to happen to really make this a reality.
So I think the work that you do, would you describe it as basic science?
Yeah, yes, absolutely.
Do you think that the current way that our society frames this basic science work versus the type of work with visible future payoffs, the type of work that industry does, for example, like whatever Uber is doing, whatever Google's self-driving car is doing. Yeah. Do you think that this is like the right narrative, or do you think that companies would actually benefit from having some sort of budget for undisciplined basic science research? Like, would it make more sense for companies to invest that way?
Well, I think we're seeing a lot of that type of investment happening. So you mentioned the self-driving car project. I think it's a really wonderful project. And that's the kind of project, the amount of resources that they're investing in this project is immense. And I think that kind of sustained effort over a long period of time is not something that you would really get in the research environment, where the grants tend to be smaller and you're sort of always looking to jump to the next thing. And yet, I think that type of effort is what's necessary to really make the self-driving car a reality, for example, to really knock down all those bugs. I think there's other types of problems where the academic research model is highly effective. It's kind of like this random walk, through all the different things we can imagine. And all of us researchers are trying different things out and sort of exploring, and sometimes we hit on something really awesome, and then that gets transferred into a product or something. The other thing that I think is underappreciated about the academic enterprise is that the transfer that happens is not always like a company or a patent that gets transferred out. Often the most important product of the academic process is people. The knowledge that an individual researcher or PhD student learns through the course of their PhD, the ways that it changed their brain and the skills that they acquired, and then they go to Google, for example. So, for example, the self-driving car project, the people who started it and many of the people who are there now were academics. Or maybe you could say they still are academics, but like, you know, they got PhDs at MIT and at CMU and at Stanford and other places, and then they went and joined this project and made it a reality. And there's many, many instances where you can point to that happening. And it wasn't like a paper that got transferred. It was a person who joined the organization. And that is the way that the impact happened sort of on the industry side. And I think that's actually the way most of this type of transfer happens, is through that process. And I think it's incredibly important to support it.
But when I think about like the IKEA robots or the forklift robots, I mean, it seems like those things, in some sense, they are basic science, but in another sense, you can think of industries that would have a distinct interest in having those projects turn to fruition. So do you think that there's any sort of future?
I think Boeing funded some of the work on the IKEA bots, assembling airplanes, right? Was their interest in it.
So do you think that will be like increasingly the norm in the future, or?
Yeah, I think we're going to see increases in both types of funding. So I think that we're kind of in the like mainframe age of robotics right now. You have these expensive platforms, robotic platforms. There's a lot of one-off robotic platforms, like Google's got their car and nobody else has it, and stuff. And we're kind of all trying to figure out like how to do different things. And I think at some point in the next 20 to 50 years, you're going to start to see a more general purpose systems, mobile manipulators that aren't just about vacuuming your floor, but that can engage in a wider variety of tasks. And as that happens, like it's sort of, I think that the cost is going to fall. So as economies of scale start to apply to this, the cost of these platforms is going to fall, and they're going to be more widely available, and that's going to increase the size of the industry, the number of people that are out there, the number and the capability of the software to carry out complex tasks. And so the field overall, I think, is going to grow.
So my final question, I saw a video of Elon Musk, and I've also seen Bill Gates talking about this, like that artificial intelligence is quote unquote summoning the demon because we're going to hit this singularity point or something where artificial intelligence will become uncontrollable. Do you think that we need to take extreme security precautions when doing artificial intelligence research?
I'm less concerned about that as a risk. I know how well my programs work, and I just don't think that that's something that's going to happen tomorrow, or even in 5 years. And I also think, we're creating, I mean, it's true that these systems can have unintended consequences, and, you can definitely imagine bad things happening as a result of, code that we've written. But I think that most people we're writing these programs to solve problems for us. And I think mostly they're going to solve problems. I think any new technology has good sides and bad sides, things that are generally considered good for the world and things that are generally considered bad for the world, nuclear power and nuclear warheads. And just like that, I think AI and robotics has that aspect. So there's, unmanned drones kill people now in Afghanistan, and that, you could argue about whether that's good or bad, but it's happening, But I think there's also immense potential for good in this technology, in helping people who are sick or who are disabled, and helping us all live more fulfilling lives, spending our time the way that we want to and not the way that we don't want to. And I personally feel the potential benefits outweigh the potential risks. And I also think the best way to understand the potential risks is to do the work that we're doing, and understanding these systems. So I think it's good we're having conversations about these risks, but I don't think it's like an existential threat that's keeping me up at night.
Great. Stefanie Tellex, thanks for coming on to Software Engineering Daily.
Sure, thanks for having me.